In many exercises there is some ball bouncing off a wall where the collision is elastic. Since the collision is elastic, the ball bounces back with the same speed. But there might be a slight confusion with this, because then it appears the momentum is not conserved. Remember, the momentum is a vector. Dealing with an elastic collision, we have conservation of momentum and energy. Each conservation law gives us an equation. From 1 and 2, we get 3 and 4. And now we divide 4 by 3 and get 5. Some more algebra. We get 6, then 7. And by substituting 6 and 7, we can isolate the final velocities, u2 and u1. Let's use this equation to investigate a few cases of two particles colliding. First, let's say the masses are equal. We get that the final velocity of particle 2 is equal to the initial velocity of particle 1, and the same goes with the final velocity of particle 1. For example, one billiard ball is moving to hit one standing one. Then the black will stop and the white one will continue in the same speed. Let's continue with v2 being 0. Equation 8 becomes this, and of course our example holds. Now let's make m1 as being much larger than m2. Intuitively, m1 should continue rolling without really feeling m2. But what will happen with m2? We get from 8 that really the big ball won't feel a thing and just continue. And m2 that was steady will gain a velocity of 2 v1. Do you have intuition why is it a factor of 2 and not 3? If yes, please let me know. Now let's do the opposite and choose m1 as much smaller than m2. We can expect the small ball to bounce back from the big ball and m2 to start moving slowly. We get from 8 that this is what happens. And if to sketch it, let's go to space and use a very small ball and a very big one. A green ball bounces back off Earth. I mean, from a yellow wall connected to Earth. So the conclusion is that this equal is only a proximity, but a good one indeed.